Okay, let's do a quick recap of what we've seen so far. So we started off with basic principles of linear algebra. We saw row reduction in the context of solving systems of linear equations. In particular, we showed that any matrix A, any rectangular matrix A, can be decomposed as L times U, where L is a lower triangular matrix and U is an upper triangular matrix. And if we do, and sometimes we may have to do column exchanges. So if P represents the matrix corresponding to column exchanges, then there exists a P such that P times A can be written as L times D times U, where L is a low triangular matrix, D is a diagonal matrix, and U is an upper triangular matrix, right? And then we looked at orthogonalization. So given a basis which corresponds to the column vectors of a matrix, the matrix A can be written as Q times R, where Q is an orthogonal matrix and R is an upper triangular matrix. So these are general decompositions. So any matrix A can be decomposed as L times U. There exists a matrix P such that P times A can be written as L times D times U, and any matrix A can be written as an orthogonal matrix Q times an upper triangular matrix R. So these are what are called canonical forms, and both the LU and all these three correspond to three canonical forms of a matrix. So these are standard forms that any matrix can be expressed in terms of. Okay, and in this in the next series of lectures, we look at another canonical form. In particular, when can a matrix be written as in terms of a diagonal matrix? Okay, all right. So, but before that, let's recall the notion of similarity of matrices. We say that a square matrix A is similar to another square matrix B if we can come up with an invertible matrix P such that B is equal to P inverse AP, right? And this essentially corresponds to a change of basis. So A is a matrix which represents a linear transformation. B is another matrix which represents maybe the same linear transformation, maybe a different transformation. So if we can write B as P inverse AP, then we say that B is similar to P. And basically what are we doing? We are changing the basis. So the columns of P correspond to the new basis vectors in terms of the old basis vectors. And essentially what we're doing is, when we are doing P inverse AP, we're first transforming the basis. So P times X is a new vector Y. So Px is a new vector which is basically representing X in terms of the original, in terms of the new basis, and this is transformed by A, and then again we bring it back to the original basis when multiplying with P inverse. And if B is equal to P inverse AP, then A is similar to B in the sense that all the properties of A are contained in B, and essentially it corresponds to changing the basis in terms of the basis vectors P. So A can be written in terms of B by just doing a change of basis, right? And therefore any change of basis corresponds to multiplication by an invertible matrix P. Okay, right. So this is the notion of similarity of matrices, and we'll use this in just a moment. So also in the last couple of lectures, we defined the determinant of a matrix. We saw some properties, then we derived this formula for the determinant of A in terms of permutations, and geometrically we saw that the determinant of A represents the volume of the parallelepiped defined by the vectors, the columns of A or the rows of A, depending on however you want to define it. Right. So let's look at the geometric interpretation of multiplication of a matrix. Now there are different ways to view matrix multiplication. So what is a linear transformation? What is the linear transformation represented by the matrix capture? Right. So essentially, as I mentioned, if A is an invertible matrix, then A represents a change of basis. But let's look at it the following way. So the three standard the standard ordered basis essentially corresponds to adjacent edges of a parallelepiped of the unit cube, right? So maybe this is the x-axis, the vector along in the x direction. This is the vector in the y direction, and this is the vector in the z direction. So these are the three standard ordered basis vectors. When I multiply by a, each of these three vectors is transformed to something else. So maybe the first standard ordered basis vector is transformed to this, the second standard ordered basis vector is transformed to this, and the third standard ordered basis vector is transformed to this. So maybe these are the three columns of the matrix A, right? So the standard ordered basis essentially represents a cube, because if you take these three as the adjacent edges of a parallelepiped, then this corresponds to the unit cube. And when we multiply by A, this essentially corresponds to the vertices of a parallelepiped, right? And it's the parallelepiped which is defined by the column vectors of A, right? And we also know that the determinant of A corresponds to the volume of this parallelepiped, right? So that's the geometric interpretation of multiplication by a matrix A. So if we have a cube, then this gets transformed by A to a parallelepiped, and a parallelepiped whose volume is equal to the determinant of A, right? So instead of a cube, what happens if we transform a sphere, right? Suppose that we have the unit sphere, or in 2 dimensions we have a unit circle. Then if we multiply by a matrix A, then the circle gets transformed to an ellipse, right? And as we'll see later, the principal axis of this ellipse or ellipsoid corresponds to the eigenvalues of the matrix A transpose A. So the original sphere, the unit sphere, can be written as x transpose x equal to 1, right? But then if we look at the transformation y is equal to A times x, then y transpose y would be equal to x transpose A transpose AX equal to 1, right? Okay, right. So the agenda for the next couple of lectures will be to somehow analyze the principal axis of this ellipsoid and see the connections to eigenvectors. First, let's see what eigenvalues and eigenvectors are. So given an n by n matrix A, we say that a number lambda, a real or a complex number lambda, is an eigenvalue or a characteristic value of A if there exists some vector in Rn such that A times V is equal to lambda times V. Right? So for this vector V, multiplication by a matrix, multiplication by a matrix multiplication essentially corresponds to scaling the matrix, right? So lambda is said to be an eigenvalue if there exists a V such that A times V is equal to lambda times V. So here lambda is a scalar, whereas A is a matrix. and such a matrix V is called an eigenvector. So this is said to be an eigenvector corresponding to the eigenvalue lambda. And well, for a given eigenvalue, an eigenvector need not be unique, because obviously if V is an eigenvector, then alpha times V is also an eigenvector, because A times alpha V is equal to alpha times AV, which is alpha lambda V, which is also equal to lambda times alpha V, right? So the set of all vectors V such that A times V is equal to lambda times V is what we will call the characteristic space corresponding to the eigenvalue lambda, or the eigenspace corresponding to the eigenvalue lambda, right? And we'll see that these eigenspaces essentially determine whether a matrix can be written in a certain canonical form or not. All right. So basically, what does eigenvalues and eigenvectors mean geometrically, right? So if we take a general vector V, so any vector V in Rn, and we try to transform this by multiplying with the matrix A, then there are two kinds of deformations that happen on the vector V, on this particular vector, right? So one, it gets scaled up or down. That is the norm of V, the norm of, let's suppose that when I multiply V by A, I get another matrix U, right? So first, the norm of U in general could be greater than or less than the vector V. So the vector V gets either lengthened or it gets shortened, right? And also it gets rotated, right? It could be rotated by a certain angle, right? So in other words, the inner product between U and V determines the angle between U and V. So note that we are looking only at square matrices A. So A times V also lies in the same space as the vector V, right? So it makes sense to talk about the inner product between U and V, and basically any vector U can be obtained by scaling V and then rotating V, right? And all possible linear linear transformations essentially do just this. They scale the vector and then they rotate it. Okay, so this is what a general linear transformation does on an arbitrary vector V. Now if V is an eigenvector corresponding to A, corresponding to some eigenvalue lambda of A, then multiplication by the matrix A doesn't rotate the vector V, it can only scale up V. So if V is an eigenvector and I multiply this by A, then I only get V scaled up, or maybe it could also be scaled down, or it could be inverted. So these are the only operations that happen. These are the only kinds of deformations that happen on an eigenvector V. Okay. So now let's see some properties of eigenvalues and eigenvectors. I claim that these three statements that I'm going to make are equivalent. So first is that lambda is an eigenvalue of A. Second statement is that the matrix A minus lambda times I is singular. And the third statement is that the determinant of A minus lambda I is equal to 0. So I want you to pause this video and try to prove this set of statements yourselves. Okay, right. So clearly, if lambda is an eigenvalue of A, then A times V is equal to lambda times V, or this is essentially the same as saying that A minus lambda I times v is equal to the 0 vector, right? So this means that v lies in the null space of a minus lambda I, and this obviously means that a minus lambda I is a singular matrix. So this is an if and only if condition, because so if a minus lambda I is singular, then lambda must be an eigenvalue of a, because there exists at least one vector v such that a minus lambda I times v is equal to 0, and therefore a times v is equal to lambda times v. And conversely, if a times v equal to lambda times v, then a minus lambda I must be singular, right? And properties 2 and 3 are equivalent, because the determinant of a minus lambda times I is equal to 0 if and only if a minus lambda I is single. Okay, that was fairly simple. But here's something perhaps slightly more interesting, and that is similar matrices have the same eigenvalues. So if a matrix B is similar to a matrix A, that is, I can write B equal to P inverse AP, then B has the same eigenvalues as A. And why is that the case? Now let's suppose that V is an eigenvalue of the matrix B, right? So right, so let's suppose that B is equal to P inverse AP, right? And what we want to show is that if lambda is an eigenvalue of B, then it's also an eigenvalue of A. So let's suppose that lambda is an eigenvalue of A. We know that lambda is an eigenvalue of A, and therefore we can write and therefore, since lambda is an eigenvalue of A, using the second property that A minus lambda times I is singular, we have the fact that, or maybe let's use the third property, the determinant of A minus lambda I is equal to 0. Okay, so the determinant of A minus lambda I is equal to 0, since lambda is an eigenvalue of A, right? So this means that so since B is equal to P inverse AP, we have that A is equal to, let me write this down later neatly. Okay, right. So we have B to be equal to P inverse AP, or A is equal to P inverse. Okay, and we also know that the determinant of A minus lambda times I is equal to 0. So this means that the determinant of P inverse minus lambda times I is equal to 0, or the determinant of P times B minus lambda I times P inverse is equal to 0, because I can be written as P times P inverse, but we know that the determinant of A times B is determinant of A times determinant B, and using this property we have determinant P times determinant of B minus lambda times I times determinant of P inverse is equal to 0, right? But P is an invertible matrix, so the determinant of P and then therefore the determinant of P inverse cannot be 0. So this necessarily implies that the determinant of B minus lambda times I is equal to 0, and therefore lambda is also an eigenvalue of B. Now similarly, we can also prove that if lambda is if say some kappa is an eigenvalue of B, then kappa must also be an eigenvalue of A, using the same set of operations, right? Okay. Okay. So given a matrix A, we want to find out what the set of all eigenvalues are. So we know that the lambda is an eigenvalue of A if determinant of A minus lambda times I is equal to 0. So we define for any matrix A, we define the following quantity, determinant of x times I minus A. So this is a function of x. So we define this to be the characteristic polynomial of A. And the set of all eigenvalues will be the set of all x such that determinant of x I minus A is equal to 0. So first, even before we get to that point, what you should convince yourselves is that this is indeed a polynomial in A. So here's an exercise. So prove that f of x is a polynomial and find the degree of this polynomial. So at least from high school you should know that the degree of the characteristic polynomial is n, since if n is an n by n matrix. But I want you to prove that the degree of f of x is equal to n. And you can use any properties that you've seen in the last 2 lectures. Okay, so now that we've seen what so now that we've seen what characteristic polynomial is and what we mean by diagonalizability and what we mean by eigenvalues and eigenvectors, let's get to the other canonical representation of a matrix that I had mentioned earlier. So we say that A is diagonalizable if A is similar to a diagonal matrix. In other words, there exists an invertible matrix P such that A can be written as P inverse dP for some diagonal matrix D. Right? And what does this basically mean? This means that there exists some basis for Rn such that so some basis, let's call this v1, v2 up to vn. So there exists some basis such that each vi is an eigenvector. Right? So there exists some basis such that each vi is an eigenvector. So in other words, we're doing a change of basis to Rn. So we want to represent all vectors as linear combinations of the eigenvectors of A, such that and we know that if A is if v1 through vn are the eigenvectors, then A times vi is equal to some scalar multiple lambda I times vi. Right? So if lambda I is the ith eigenvalue, then we say that vi is the ith eigenvector and A times vi is equal to lambda I times vi. Right? Okay. So we say that so this is third canonical form apart from the LDU decomposition and QR decomposition. This is the eigenvalue decomposition where A can be written as P inverse dP. Right? But here this leads to the following question: is every matrix diagonalizable? That is, given any square matrix A, can we always write it as P inverse dP for some invertible matrix P and diagonal matrix D, right? So it turns out that that is not the case, right? So there exist matrices which are not diagonalizable, and here is one simple example. So let's take A to be equal to 1 1 0 1. So I claim that this matrix is not diagonalizable. So I want you to pause this video and try to work out for yourself and think how do you prove that A is not diagonalizable. All right. To show that A is not diagonalizable, we have to show that this set of equations, that is A equal to P inverse dP or PA equal to dP is not solvable. So this does not have a solution for any invertible matrix P and diagonal matrix D. So what does that mean? So it means that there exists no alpha, beta, gamma, delta and diagonal and numbers D1, D2 such that which satisfy this equation, right? So if there exist numbers alpha, beta, gamma, delta, D1, D2 which satisfy this equation, then it means that this matrix is diagonalizable, right? So let's simplify this. So we have alpha and alpha plus beta and gamma plus delta should be equal to D1 times alpha, D1 times beta, D2 times gamma, D2 times delta, right? So if a solution exists, then this set of equations must be satisfied. Now let's equate these term by term, right? So alpha should be equal to D1 alpha equal to D1 alpha and gamma equal to D2 gamma must necessarily imply that either alpha equal to 0 or D1 equal to 1 and gamma equal to 0 or D2 equal to 1. Okay. Now similarly, if let's equate the second set of equations. So we have alpha plus beta to be equal to D1 times beta. So now there are 4 conditions. So either alpha equal to 0, gamma equal to 0, which is not possible. If alpha equal to 0 and gamma equal to 0, then it must mean that this matrix is not full rank and therefore it is not invertible, right? So let's assume that so if alpha equal to gamma equal to 0, then alpha, beta, gamma, delta is a non-invertible matrix. So that option is completely ruled out. So now suppose that D2 is equal to 0. So let's suppose that D1 equal to 1. So D1 equal to 1 implies that alpha plus beta equal to D1 times beta, which is, since D1 is equal to 1, alpha plus beta should be equal to beta, or this means that if D1 equal to 1, then alpha should be equal to 0, right? So no matter how you choose, so irrespective of whether you choose alpha to you say that alpha is equal to 0 or D1 equal to 1, this always implies that alpha is equal to 0. Similarly, D2 equal to 1 must mean that gamma plus delta equal to D2 times delta, which is delta. this means that gamma equal to 0. So for this set of equations to be satisfied, we must have alpha equal to gamma equal to 0, and this means that this matrix P is non-invertible, and therefore this set of equations can never be satisfied, and hence A is non-diagonalizable. So this was just a simple example, and you can construct more complicated matrices which are not diagonalizable. So the questions we would like to address in the next couple of lectures are the following. The first is, when is a matrix diagonalizable? So what are the conditions for a matrix to be diagonalizable? The second question is, okay, suppose that a matrix is diagonalizable, how do we find the eigenvalues and eigenvectors of the matrix A? Right? So we'll try to answer these questions and more in the next couple of lectures.